Reed-Solomon codes, enhancing data reliability through algebraic coding theory. Introduction. Reed-Solomon, RS, codes are a pivotal class of error-correcting codes that have significantly impacted digital communications and data storage systems. Introduced by Irving S. Reed and Gustav Solomon in 1960, these codes enhance the reliability of data transmission over noisy channels by enabling error detection and correction. RS codes are used across various domains, including QR codes, CDs, DVDs, Blu-ray discs, and satellite communications. This essay explores Reed-Solomon codes within the context of algebraic coding theory, highlighting their importance, functionality, and applications without delving into complex mathematical equations. Basics of algebraic coding theory. Algebraic coding theory focuses on constructing codes that efficiently detect and correct errors in digital data. A code is a set of symbols used to encode information so that any errors introduced during transmission can be identified and corrected. Error-correcting codes leverage algebraic structures, such as polynomials and finite fields, to design codes with robust error-correcting capabilities. The two primary objectives of coding theory are to maximize the amount of information transmitted and to minimize the error rate. Achieving these goals involves a trade-off between redundancy, extra bits added to detect correct errors, and efficiency, the proportion of information bits to total bits. Reed-Solomon codes excel in this trade-off, providing powerful error correction with relatively low redundancy. Reed-Solomon codes, an overview. Reed-Solomon codes are non-binary cyclic error-correcting codes constructed using finite field arithmetic. They are characterized by their ability to correct multiple random symbol errors within a block of data. Unlike binary codes, which operate on individual bits, Reed-Solomon codes operate on symbols, typically comprising multiple bits, for example, 8-bit bytes. This symbolic approach allows for greater flexibility and more efficient error correction. An RS code is denoted as RSNK, where N represents the total number of symbols in the code word, and K represents the number of information symbols. The difference, NK, indicates the number of parity symbols, which provide the redundancy needed for error correction. The maximum number of correctable symbol errors in a code word is given by T equals sign, NK/2. This relationship demonstrates the trade-off between the code's length, the amount of information it can carry, and its error-correcting capability. Encoding and decoding. Encoding involves transforming the original information symbols into a longer code word by appending parity symbols. This process ensures that even if some symbols are corrupted during transmission, the original data can be reconstructed. The encoding process uses generator polynomials defined over finite fields to systematically generate parity symbols. Decoding is the process of retrieving the original information symbols from a possibly corrupted received code word. This involves identifying and correcting errors. Reed-Solomon decoding typically consists of three main steps. 1. Syndrome calculation. This step checks whether the received code word has errors by evaluating it against a set of parity check equations. The resulting syndromes indicate the presence and nature of errors. 2. Error location. This step determines the positions of the errors in the received code word. Various algorithms, such as the Berlekamp-Massey algorithm, are used to solve for the error locations. 3. Error correction. Once the error locations are known, the magnitude of each error is calculated, and the errors are corrected, resulting in the retrieval of the original information symbols. Applications of Reed-Solomon codes. Reed-Solomon codes are incredibly versatile and find applications in numerous fields due to their robustness and efficiency. Here are some notable applications. 1. Digital storage media. RS codes are extensively used in CDs, DVDs, and Blu-ray discs to ensure data integrity. These media are prone to physical damage, such as scratches, which can corrupt stored data. Reed-Solomon codes enable the recovery of original data by correcting errors introduced by such damage. 2. Data transmission. In telecommunications, RS codes are used to correct errors in data transmitted over noisy channels. For example, They are integral to the error correction mechanisms in satellite communications, where data can be distorted due to atmospheric interference. 3. QR codes. QR codes use Reed-Solomon codes to store data robustly. The redundancy provided by RS codes allows QR codes to be scanned accurately, even if they are partially damaged or obscured. 4. Networking. In computer networks, RS codes are employed in protocols like Digital Subscriber Line, DSL, and Wi-Fi to ensure reliable data transmission. They help maintain data integrity by correcting errors that occur due to signal degradation or interference. 5. Space communications. Space missions, such as those conducted by NASA, utilize RS codes to protect data transmitted over vast distances, where the likelihood of data corruption due to cosmic noise is high. These codes ensure that critical information reaches Earth accurately. Advantages of Reed-Solomon. Codes 1. High error correction capability. Reed-Solomon codes can correct multiple symbol errors, making them suitable for environments with high error rates. 2. Symbol-based operation. Operating on symbols rather than bits allows RS codes to handle burst errors more effectively, which are common in many real-world scenarios. 3. Flexibility. RS codes can be designed to meet specific requirements by adjusting parameters such as the code word length and the number of parity symbols. 4. Efficiency. The algebraic structure of RS codes enables efficient encoding and decoding algorithms, which are critical for real-time applications. Challenges and limitations. Despite their advantages, Reed-Solomon codes also face certain challenges. 1. Complexity. The mathematical operations involved in encoding and decoding, particularly over finite fields, can be complex and computationally intensive, especially for large code word lengths. 2. Error burst limitations. While RS codes are effective against burst errors, they may not be as efficient in correcting very long burst errors that exceed their correction capability. 3. Hardware implementation. Implementing RS codes in hardware, such as integrated circuits for real-time decoding, can be challenging due to the need for specialized arithmetic operations. Conclusion. Reed-Solomon codes are a cornerstone of algebraic coding theory, offering robust error correction capabilities that have made them indispensable in various applications. Their ability to correct multiple symbol errors makes them particularly valuable in digital storage, data transmission, and many other fields where data integrity is paramount. Despite the inherent complexity of their mathematical foundation, the practical benefits of RS codes far outweigh the challenges, ensuring their continued relevance in advancing technology and communications. As the demand for reliable data transmission and storage grows, Reed-Solomon codes will remain a critical tool in the ongoing effort to enhance data integrity and communication efficiency.